This is the first of a series, all based on high voltage DC. So this all began with a 19th century debate whether DC, direct current, or AC, alternating current, was the right technology to use for the transportation of electricity and the use of electricity. Now, there's a gentleman by the name of Thomas Edison who was first to the market with his 110-volt DC system. As a result, building up an established base. 110 was used as it was slightly higher than the 100-volt incandescent lamps at the time, and the DC motors that were driven from it. DC is okay in that you can parallel sources and store energy, whether it's in battery form or capacitor form. However, at the time, with 19th century technology, very, very difficult to step up or step down the voltage. As a result, transmission was very lossy, and it meant that a power station had to be within 1 mile of your home or your factory, otherwise you didn't get good electricity. Also, due to high power at a low voltage, you have a high current, and there were some unfortunate incidences, such as a great storm in New York in 1888, in which snow brought down power lines and several people were electrocuted because of the high current on the hidden cables in the snow. So then along came a young man called Nikola Tesla, who was working for the Westinghouse company, and he was a big fan of the AC distribution. And AC is very good because you can step up the voltage easily using a simple transformer and therefore transmit power over longer distances without losing as much energy. Also at the same time, new motors, new lights were invented to act as the loads in this system. So what we have is we have a very huge and public battle between these two technologies. It's the Betamax versus VHS of its day. And in the end, there were technical questions, commercial questions, a lot of political goings on. But in the end, by the mid-1890s, that was all resolved in favor of AC distribution. A significant point being an exhibition in Germany in 1891, which proved that three-phase AC distribution was the more economical for transmission. And also, in parallel with that, and as part of that, the emergence of General Electric and Siemens as huge companies with a broad variety of different loads, motors, switches, lights, generators, etc., that could put the whole system together for AC. However, we can't forget Topsy the elephant. Topsy the elephant was very anti-AC power. Actually, Topsy was the unfortunate animal. Edison, to prove that AC was very bad, promoted the use of AC power to unfortunately kill an elephant in 1903. And unfortunately, Topsy and also people in the New York penitentiary were killed using AC power, driven by Edison's desire to prove its danger. However, in the real market, everyone went onto AC, and that's the way it's been ever since, until we go from a 19th century debate to the 21st century, and we have various catalysts which reopen the debate about AC or high voltage DC distribution. These are everything from global warming, government regulations, the cost of electricity, and in many respects, changing loads. Hybrid vehicles work best on a DC power supply. Various sources, for example, wind or wave power, generate a DC power supply. And at the same time, we have changes in the marketplace in terms of loads like your telephone. In the old days, a telephone was a device to do audio communication. Now a telephone is the triple play of voice, video, and internet, which increases the traffic, which increases the amount of processing which needs to be done on that information. And all of those loads, those switches, routers, server units. Everything runs on DC. So really it's a case of, can we revisit the high voltage DC to make that very effective in the marketplace? The last one on this list is actually one of the most important. The fact that now we have standards and systems and components which are available to actually create real high voltage DC systems. So in the past, this might have been an academic question. Now it's very much an industry accepted movement. So we had a 19th century debate, 21st century catalysts, but we also need to consider 21st century pragmatism. There are various questions we need to ask in whichever application it is to say, is high voltage DC the right thing to do, and is now the right time to do it? This depends on the kind of work that for example, if this is a data center, the kind of server is doing. Is it number crunching and predicting the course of a hurricane, or is it simply looking at a video of a kitten on YouTube? So different loads mean different power levels per rack, mean different distribution choices. We've got installed bases. For example, in Vicor we have two main sites, and we have small data rooms, I wouldn't call them data centers, in each location. Now they right now run on an AC power outlet, and due to the small size, it wouldn't make commercial sense for us to tear up that AC system and put in a DC one. However, if you're building from scratch a new office block or school or library or factory, then now is the time to consider 380 volts DC from the start, and hey presto, you can plug in your 380 volt DC server. So lots of different choices which need to be made, lots of conditions that need to be met before we can look at whether AC makes sense or high voltage DC makes sense. And the chart on the right shows a question mark about the adoption of high voltage DC compared to AC, but I think there will be a home for both versions as we move forward. When it comes to high voltage, there are various definitions of what we mean by high voltage, and unfortunately, we as an industry, whether it's the very high power transmission or it's the low power usage of electricity, don't agree what we mean. So between the ETSI, the ANSI, IEC, we have different definitions. So pragmatically again, for this webinar series, we're going to use high voltage to mean anything between 60 volts and 1 kilovolt. It is an arbitrary vernacular use of high voltage. I apologize if you're an aficionado of any one of these groups and we're breaking the rules, but high voltage DC is what we're using for 60 to 1 kilovolt. So the benefits of high voltage. The first one comes back to Joule. Joule figured out that the loss in a conductor, or rather resistor, is based on the square of the current times that resistance, usually expressed in watts, and obviously this applies to DC or AC distribution. So simply it's the power loss is the square of the current times the resistance, which means that for the same amount of power, if you can keep the voltage as high as possible and get it as close to the load as possible before you need to step down, you will have the most efficient architecture. So on the drawing on the right-hand side, we're saying, okay, we've got an AC through PFC system to 380. If you drop down to 12 volts at that point, you're wasting a lot of power, and also if your final conversion to 1 volt is a distance away from the load, you're losing power again. But if you can maintain that high voltage, and also we can suggest some new high power, high efficiency converters, you can save a lot of energy and have a much simpler system. Obviously, the less power you lose on the way from your source to the load, that's less heat that you must air condition away, again saving energy on the air conditioning. So one of the benefits is simply down to Joule's law. Keep the voltage high, keep the current low, your losses will be low. The second benefit is down to the finances. And this table is from a presentation made by a group of companies at the Intellect 2013 conference in Hamburg, in Germany. This paper was a combination of HP, Juniper, Emerson, and Vicor. I apologize if I missed somebody off there. And this is the culmination of different studies by Orange Telecom, by China Mobile, by Lawrence Berkeley National Labs, etc., on how we can save money by installing and using a high voltage DC system. In this case, obviously, it's a data center focused study. So when it comes to CapEx, the original building, by eliminating the uninterruptible power supply, that's the UPS, and reducing the amount of copper that you need for the distribution, you can save 15% on your building cost. OpEx, this comes down to how efficient is the system for the work it does, and obviously the price of electricity in dollars or euros per kilowatt hour. Space reductions, when we talk about data centers, it's how much functionality per square foot can you do. So that's a big area there. And a difficult one to quantify, but definitely power quality is a huge bonus for high voltage DC. If you take three-phase AC into the edge of a building and then convert down to high voltage DC for the rest of the transportation and conversion of that power, you don't need to worry about any phase balancing or any lost or abandoned power that you would have in a typical three-phase system. That's the kind of thing where high voltage DC makes a lot of sense and makes it very, very simple. And we also need to look at the practical side of high voltage DC as well. So, as I mentioned earlier, wind, solar, power, those are DC outputs. And the loads themselves are DC inputs. So if we can match up the sources and the loads together in one place or in terms of a microgrid, then that is a very efficient and elegant way of transporting and using valuable power. Another example of practicality is in aircraft. So with aircraft, you have traditionally jet engines or previously propeller engines that obviously have a mechanical rotational energy, which is then converted to electrical power through a turbine or a generator. Now, one of the issues with this is that as the engines speed up and slow down, whether takeoff, landing, or in combat, and whether one engine is running faster or slower than the other ones, you can have a clash of frequencies unless you somehow control that frequency. And traditionally that was done with a thing called a constant speed drive to create a 400 hertz output. But that is a physical drag on that jet engine or that petrol engine, therefore loses efficiency. If you can rectify the AC that's coming from each individual engine and use it to create a 270 volt DC rail, those can be tied together, and therefore you don't have to worry about which engine is actually running faster or slower, higher power, lower power than anything else. And by doing that electrically rather than mechanically, you improve the efficiency of the whole system. So if we take the Airbus A380 as an example, that has a 150 kilovolt amp power requirement that it takes from its engines and uses 270 volts to bus that power through the aircraft. So powering everything from seat motors in first class to the TV still in the economy section of an A380. So a lot of load in an aircraft. And thinking about power and also the distance, again, going back to Joule's law, picture of a Dreamliner 787-10, which is a new version being brought out by Boeing. That is 68 meters long, and that's a long way to transmit power if you were doing a low voltage. So definitely the high voltage, again, Joule's law means that 270 volts is the way to go. So those are some benefits of high voltage, but some of the main questions are, well, how do we use that high voltage? How do we transport it, and how do we convert it to something else that's useful? And for Vicor, we have a concept which is the power components methodology, by which we provide high efficiency, small size, flexible building blocks, much in the way of Lego toys. By having a small number of building blocks, they can be arranged in different ways to architect different systems for different markets and applications. So for example, within those building blocks, those mechanical packages, we could have the SAC, which is a sine amplitude converter, which is a kind of isolated transformer, which we'll come on to in a moment. We could have buck boost. We could have regulated, non-regulated, AC input, DC input, high voltage, low voltage, etc. And we can parallel those building blocks for more power, or we could, for example, stack the outputs to get improved higher voltages. So very flexible Lego building blocks to make advanced systems. And mechanically, those devices are dual-sided PCB assemblies with surface mount components. We have planar magnetics. We use latest generation of silicon, be it controlled silicon from NXP or Silicon Labs, or if it's FETs from ST, Fairchild, Infineon, a broad range of components. And also, by having these distinct blocks of maybe a transformer and then a separate regulator, we can use latest technology components as and when available to improve the performance of the transformer independent of the performance or run rates of the regulator. Also, we can make components run at different frequencies. We can have different sizes of package. It's a very flexible system, and that flexibility is amplified when we look at architectures. In terms of power capability, we're really looking at things that within a 2 square inch area, we're now up to processing 1500 watts as an isolated transformer, going from, say, 380 volts down to 48. So very high efficiency, very high power density building blocks, a flexible approach to many different architectures. So a heads up on what's going to happen next week. December 12th will be a deep dive on the technical aspects of 2 components, one of which is this non-isolated buck-boost converter, and then the next one is the isolated transformer. So if you're a real engineer at heart, you'll enjoy next week's presentation a great deal. If you're more on the business side, it's okay to miss next week. You can come back to the market and application specific seminars that we'll be doing in January, February, and March. So if this was a lecture, it's okay to miss next week's lecture for that one. So the component building blocks. The first one is this non-isolated buck boost. Obviously, we have an arrangement of MOSFETs, and depending whether the input voltage is lower or higher than the desired output voltage, you are either boosting upwards or bucking downwards using different switching cycles of the MOSFETs. Now, one key aspect of this converter is that it is a zero voltage switching system, which means that there is, when we turn the MOSFETs on and off, we don't have any trapped gate charge within the physical semiconductor of the MOSFET, which means we can turn these devices very quickly on and off at high frequency without any loss being generated within the device. This ability to go high frequency, coupled with new magnetics, means we can go to smaller transformers and inductors, which means that we can reduce the size of our PCBs, which reduces the impedance, which reduces the parasitic losses. There's a positive spiral of innovation, which means that we have some very efficient buck boost regulator devices. So that's a regulator, non-isolated. That is used in conjunction with an isolating transformer. Now, if this kind of device was available in Edison's time, we might be facing a different installed power distribution base. This is a DC to DC transformer. So a DC voltage is applied on the primary. We have a full bridge in this example, which creates a pure sine wave, which leaps across the transformer gap and then is rectified again using MOSFETs back to a DC level. So for example, if we had an input of 380 volts and a transformer ratio, a K factor of 1 divided by 8, then we go from 380 to 48 volts on the output. Again, this is zero voltage switching and also zero current switching in all of the different cycles, which means very high frequency, in this case up to 1.7 megahertz on the primary switching frequency. This particular topology is a LC resonant. So LC refers to the tank in which charge is stored during the switching cycles. And the L in this case, the inductor, is the leakage inductance of the transformer. The C, the capacitance, are physical capacitors within the module. And one key feature of this is a fixed frequency resonance system. Unlike other resonance systems which have a dithering frequency, this is fixed frequency, which means that it is very easy to identify and filter the primary switching peak. Another thing about both the regulator and the transformer is that due to the zero voltage switching and zero current switching, we have very controlled waveforms. There are no hard switching spikes, which means that in terms of EMI, very easy to filter with small and low-cost components and small size and weight components. Also, the fact that we don't have major spikes means that we can use lower resistance MOSFETs because of lower voltage headroom and still have, and that reap the benefit of that low RDS(on) as well. So we're now at the stage where we can have some 1500 watt devices in that 2-inch square area devices. We've had what we call the VI chips released for 10 years now, and we are soon to release a new package format and a next generation of the chips called the chip, which is converter housed in package. So we made a technology announcement about that at APEC this year. You'll be seeing some product release announcements very, very soon, and this is a heads up on some of the capabilities of those products. So those are the two basic building blocks, and again, next Thursday we'll go into a deep dive technical review of those. In the meantime, let's look briefly at some case studies. So you can see here, these are the case studies that we'll be going through in the new year. Variety of voltages ranging from 270 volts up to 800 volts DC, and covering quite a broad range of the market. So the first one is the DC data center, and one focus for high voltage DC in the data center is that they use a lot of power. Right now, somewhere between 1.3 and 1.5% of the entire electricity in the world is going into data centers, and that is only increasing with the rise of what we call exadata. Now, in 2010, that translated as $35 billion worth of electricity bill based on a 14-cent kilowatt hour. Again, into perspective, we've got Google using 300 megawatts and Facebook already using 60 megawatts of power. Now, these companies realize that this is a huge issue, and this is why in various forums this kind of company are moving to, or at least discussing, high voltage DC, especially when it comes to the link with renewable energy. Facebook have declared that their new data center opening in Iowa in 2014 will be 100% wind powered. Now, I don't know the details about how they do that. I know it's windy in Iowa, but sometimes the wind stops. I'm sure they've got backup systems in place, but they have declared 100% of the power would be provided by wind. Now, we mentioned the exascale word earlier. An exa is 1 times 10 to the power 18, and that's a lot of zeros. So the challenge, the exascale challenge, is in the US, and the Department of Defense said, we need a data center that can do an exaflop, so that's 1 times 10 to the 18 floating operations per second. And the Department of Energy said, that's fantastic, but you can only have 20 megawatts to do it. So when we look at what we can do today, and we look at, for example, in 2012, the most efficient computer in the world was the Blue Gene Q machine from IBM. And Vicor was very happy to participate in that, providing power to the processors and the memory. The exascale machine needs to be 25 times more efficient than that to meet that challenge. So it's a big one for all of us in the industry, whether it's improvements in the processor, but definitely improvements in how we provide those silicon chips with power, distribution and conversion challenges. Now, when it comes to voltage specs, huge breakthrough probably 18 months ago now, with the publication of 2 specifications specific to high voltage DC. One coming from ETSI, that's the European Telecom Standards Institute, and one from the ITU, that's the International Telecommunication Union, which dictate exactly what we mean by 380 volts. What is the normal operating range? What is the wider operating range? And then what is an abnormal or fault condition? In association with those specifications, we also have groups like the eMerge Alliance and the Open Compute group. And Open Compute, if you're not familiar, is a group of people largely driven by the Facebook team, looking at ways to have efficient and also very cost-effective racks for generally lower power processing. The spec, as originally written, was up to 14.2 kilowatts in a 19-inch rack. That is now being rewritten with an additional 380-volt DC input to that specification. So that kind of open compute project is also having a high voltage DC input. The associated specs, those relate to the plugs, the sockets, the bus bars, the power conversion blocks, the drop boxes, everything that relates to the infrastructure of the system. And we'll be going into more information on those during the market-specific seminar. And just in case we don't know what we mean by high voltage DC within a data center, this is an image that I've taken from NTT. And traditionally, with an AC system, you would have AC to DC as part of the UPS, back up to AC, then again AC down to DC, and various steps to the load. We combine, or we move from that, and we look to the right-hand side, and a traditional telecom central office system is AC to 48-volt DC, and we keep it there until we need it. However, 48 volts is not high voltage enough to avoid lots of loss according to Joule's law. So the combination of these two gives us our high voltage DC data center. So we take in AC from the very high voltage outside the walls as it's delivered by the power company. But once we convert that down to a high voltage DC 380, and at that point do battery backup, we keep it at 380 volts until we need it. So that's how the high voltage DC system came about. Now, one of the issues is that while we might have creation of 380 volts DC data centers, it may take a while before the loads are available that plug directly into that 380 volts. Now, right now, we've got systems from HP and Juniper which go straight into 380 volts, but there are a lot of machines, switches, routers, servers, which rely on a 48 volts or a 12 volt input. So one question is, how do we get those legacy loads into a new high voltage DC system? So the table on the left-hand side, or rather the y-axis, is taken from the ETSI high voltage DC spec. So you can see that there's a 380 volt expected operating point, but then a wider range around it before we get into the red zone, which is the abnormal condition. So if you have 380 volts on the input and you want 48 volts on the output, it's simple. Put in a transformer, our bus converter module, with a transformer ratio of 1 divided by 8. Job done, high efficiency, very easy. However, if something happens to that AC power and the voltage on that high voltage line starts to decay, then simply transforming is not enough, and this is where the buck boost regulator kicks in to boost back up to that 48 volt level. So you can see in this case we've got two building blocks, those Lego bricks, one of which is the transformer, one of which is the regulator, that together form a very elegant, simple, high efficiency system. And while we're looking at the data center area, we also need to think about people moving away from traditional 12 volt distribution on the motherboard up to something higher. Now, putting 380 volts onto a motherboard is possible, but getting that very close to the processor really starts to get people worried. However, we do have an established 48 volt direct to processor combination, originally pioneered in the telecom market and now adopted also in the server market, to convert that power from 48 volts very efficiently down to 1, 1.8 or 0.9 volts. And here you see a quick snapshot on some of the Intel-based reference designs where the Vicor units are providing very efficient, very low-cost power from that 48 volt rail down to 1.x volts. And again, we'll go into more detail on that in the market-specific webinar. Another area for 380 volt DC is in buildings themselves. So if you're building a new school or a library or a factory, then a group called the DCC&G, so this is the DC, direct current, components and grid consortium. This is based largely in Europe, but there are also other international members. And the real key here is that around the Fraunhofer Institute in Germany, but obviously big companies like Emerson, Siemens, Philips, etc. are all part of this group. And the premise is, with a clean piece of paper, can we design a high voltage DC building and save money in running costs, save money in construction costs, and have the infrastructure in place and the loads in place to make it a practical system. So the diagram here on the bottom left shows how a plus or minus 380 volts around a middle point can provide varying voltages, either 380 or the 760 volts, to different DC loads, or obviously if there are some legacy systems requiring AC, you can have some very low power AC lines running around the building. Again, this helps where, as well as the AC mains coming from the left-hand side, you can also have photovoltaic from the right-hand side, making a small microgrid. On the right-hand side is an example of the Vicor bus converters. We have two units here with a transformation ratio of 1 divided by 32. So that means with 380 on the input, we get 12 volts on the output. However, you can stack those outputs like Lego bricks and get 24 volts. And that is being used as a microgrid within rooms to provide power for laptops, LED lights, that kind of thing. So this will be the second of the seminars in the new year. So this is high voltage DC in the building, the real infrastructure of it. Now then, let's take a look at things that fly. We mentioned the A380 and the Dreamliner earlier. So 270 volts applies to a large variety of craft. And the key factor here is swap. This is the size, weight, and power. Obviously, the lighter the unit, the less fuel is required to take off, the longer the flight. If you don't have as much physical size, you can make the unit smaller, or you can carry more other things, whether that's people or it's payload. So all of these elements come into play, and the real one for the aircraft industry is this low weight idea. Now, the voltage specification for aircraft is the MIL standard 704F, and we also have associated standards for EMI, conducted and radiated emissions, for reliability specs and things like that. So we'll be going into the MIL standard 810, 461, 883 specifications as we go through in the new year. One example of part of the case studies that we'll be looking at in detail is in terms of radar. So radar, a very high power usage within aircraft. Coming from 270 volts, how do you get down to, for example, a 2.5 volt silicon germanium transmitter, or maybe a 28 volt, 30 volt, 52 volt gallium nitride unit? Various different loads that are required in different radar applications. So the first thing is we need high efficiency conversion down to those loads. At the same time, the components, those building blocks, the Lego brick of the transformer, the DC-DC transformer, and the Lego brick of the non-isolated regulator, those play together to reduce the amount of system capacitance required in a pulse power output. We can right-size the powertrain for the average power, but also the DC transformer is a thermally limited device rather than a power limited, which means that depending on the cooling and the length of the pulse, we can do a 2 times overpower rating. So if you have a pulsed power application, you don't need to size the powertrain for the peak amount, simply the average amount. And with the soft switching, with the high frequency, all of these issues factor into having a very, very small EMI footprint and therefore easy to filter. And what that means is, for a typical silicon germanium pulsed radar application, the power conversion system, including the capacitance required for that pulse power, is 8 or 10 times smaller and lighter than using traditional systems. So an excellent example of the size, weight, and power being critical in aircraft. Now, back on land, we have some heavy-duty vehicles, and the picture here is not a tank. I'm told this is a self-propelled howitzer. So it's an example of the kind of equipment into which a new voltage spec for military equipment, this is the GCS 600A, is being applied. So the GCS 600, that's the 600 volt nominal distribution spec. Again, we've got EMI and reliability specs around it. And within this Paladin unit, this howitzer, traditionally hydraulics were used to control the gun turret in terms of twisting around and also raising and lowering the gun barrel. But now in the next generation, those systems have gone into electric drives. And there are several good reasons for this. One is that the new electric drives are lighter and more reliable than the hydraulics. The other element is that if an electric drive goes faulty, it can be taken out and replaced with a spare by the tank crew without the unit having to go back to base and being fixed. So this 600 volts is generated from the diesel engine, used to provide power to those motors, and also we need to convert down to a 28 volt battery because you need your satellite navigation, you need computers, you need various motors. So we need a converter going from that 600 volts down to 28. We also need it to work in reverse because that generator coming from the diesel engine is also the starter for the diesel engine. So starting the engine from cold, power is taken from that 28-volt battery and boosted back to 600 volts to kickstart the motor. And this fix in the field and easy maintenance is also part of military TCO, or total cost of ownership. And if you're interested in more information on that and how different governments are looking at specifying, procuring, and maintaining devices, then the UK government is a good example, working with suppliers not only to say, we want this and we want it on this date, but how reliable will it be, what are the running costs, what is my availability over the next 10 or 15-year period. So there's a reference here for the UK defence. Now that's the military land-based, but there's a much larger market in the commercial land-based equipment. A very interesting spec came out from Komatsu, the Japanese earth-moving company, that only 13% of the energy from the diesel fuel in an earth-moving piece of equipment is actually applied to moving earth. The rest of it is wasted in heat, in the hydraulics, in idling. So Komatsu have worked with different systems to reduce the amount of diesel required to do a certain function. Now, as with the automotive world, there are various forms of hybrid. There can be some pure electric units, for example, forklift, or some small diggers. There can be hydraulic hybrids, but the one we're interested in is the electric hybrid. And the areas for power, obviously, is recovery of inertia, going to electric motors versus hydraulics, very lossy, and also those auxiliary functions from electrical power. For example, if you're in the middle of the desert on a construction site and you want to stop to have your lunch, then you can turn the diesel engine off to save fuel, but it gets very hot. You want your air conditioning to work. So while you're having lunch, power for the air conditioner comes back up from that 28-volt battery or 24-volt battery to the higher voltage point to run the air conditioner. And the middle drawing on the right there, that's a very high-level schematic of a reversible 800-volt down to 24-volt unit using, again, the DC to DC transformer and buck-boost converter units. Now, when it comes to the various powertrains within the hybrid systems, we've got two main ones. Obviously, there's the 600 to 800 volts from the diesel generator itself. But also, if we imagine if we are a digger, or you are a digger, you reach forward and pick up a handful of earth, and if you rotate left or right, it takes energy to start that move, and when you come to a standstill, usually you lose that energy, which is, in a traditional system, lost in hydraulics or springs, some mechanical loss. However, Komatsu have a very bright idea that if you have motor alternators to drive that rotation, as you come to a standstill, that rotational energy is boosted back up from that motor to some ultracapacitors. And when that energy is required again, the ultracapacitor releases that power back into the motor and continues the rotation. So a very interesting way of using the ultracapacitors to save energy. And Komatsu's hybrid, the result is that they claim 25% reduction in fuel cost and also in CO2 emissions, which we all appreciate. And that means that that usable energy from the diesel goes from 13 up to 18%. So might not sound a lot, but that's a huge advantage in this kind of market. In traditional car or truck hybrids, or actually even locomotives now, hybrid engines are being used to do propulsion regenerative braking, have auxiliary systems, and this is now obviously taking off in a big way. And some forecasts have a 30% share of an electrified powertrain by 2025. If we also include the start-stop mechanism, which is where if a vehicle comes to a standstill at a traffic light or a stop sign, the engine turns off completely. And then when you need to go again, you touch lightly on the accelerator pedal and the engine starts up again. So that needs a small electrical helper system to do that. And that's called the LV 148 is the name of the spec for that stop-start system. In general, automotive or truck applications, lithium-ion batteries can vary anywhere from 160 up to 420 volts. That's for the main powertrain. However, again, you still need your satellite navigation, you need your radio, you need your seat motors, your rear view mirror adjusting motors, heavy load in any vehicle. So somewhere between a kilowatt and 3 kilowatts of 12 volts or 24 volt power is required. Again, here we're looking at some very high efficiency, high density units. The picture on the bottom left is a slice through a high voltage DC down to 12 volt 2.4 kilowatt converter using some Vicor components that are called DCMs. These are regulated and isolated down converters. So you can see we've got a large range of hybrid applications, whether it's locomotives, whether it's trucks, whether it's supercars. That picture of the McLaren on the bottom right there. McLaren should be introducing an electric supercar next year, and I look forward to seeing what that looks like. So, to wrap up, that was a very brief introduction to high voltage DC. We've looked at the origins, we've looked at the 21st century catalysts, and some of the equipment that's available now. We'll be going into a lot more detail on the power conversion components next week. That's the DC-DC transformer and the buck boost regulator. And then we'll be going into application or market-specific examples, taking around 45 minutes or an hour in each of these areas, starting with the data center, January 30th, and moving through the different examples. We will be combining, as you'll see on February the 20th, the 600 volt and 800 volt heavy-duty equipment. They share similar topologies, similar architectures, so we'll be grouping those two together in one. But overall, we'll be having 5 market-specific seminars in the new year. Each one of those will obviously have a market overview. There will be the core specifications and related specs as well. We'll look at different issues in power conversion and distribution and associated things like filtering. And we'll have the worked examples with efficiency, size, and weight as appropriate.